Okay, today we're going to talk about chemical reactions. Chemical reactions are a way to visually describe chemical equations. So it's a visual representation of a chemical reaction or a chemical equation. Okay, so chemical reactions are when one or more things react together to form one or more different types of things. And to do that, you have to rearrange chemical bonds. That's a reaction. So now that we've talked about what atoms are and what they're made up of and their different valence electrons, then now we're going to talk about, once we mix these things together, what happens when they start to chemically react? What happens when we rearrange these chemical bonds? And we're going to be able to show this with what is called a chemical equation. And it kind of looks like a math equation. So you're going to have some stuff on one side. So for instance, you have maybe one carbon on one side and you react it with one oxygen. Oxygen is one of our diatomic molecules. It likes to exist in pairs because of the way that it shares valence electrons. And when we react together that one carbon and that one oxygen molecule, we get one molecule of carbon dioxide. Okay? So this is what a chemical equation looks like, and I want to spend a little time talking about kind of the anatomy of the chemical equation, if you will. Okay, so what we have over here, these are ones. I wanted to make sure that was clear that they were ones and not just a slash for a one. What we have over here on the left-hand side of the equation, so my carbon and my oxygen are called my reactants. These are the things that we react together. So we put them together in a reaction vessel, and then these reactants form, and that's what this arrow kind of tells me, sort of like a mathematical equation. The arrow kind of represents an equals sign. These reactants form products. So we can kind of think of this as forms or equals, okay? Or goes to is another way that you'll hear it. So reactants go to products, reactants form products, reactants react together and equal products, however you wanted to think about it, okay? All right, so everything on the left-hand side are called your reactants, everything on the right-hand side are called your products. Now let's kind of look at the different details within these. We know that these little numbers right here, the little numbers below, are called subscripts, and they tell us how many of that atom are in that particular molecule or compound. So this says that we have 2 oxygens for every 1 carbon. This says that we have 2 oxygens, and there's no subscript here for carbon, so it's just 1. If there's no subscript, it just means that there's one of that atom or one of that atom within a compound. So the little numbers are called subscripts. Okay, so those subscripts are the little numbers that tell how many of that atom are in the molecule, 2 of my oxygens. Now these bigger numbers out front, so the ones, they're all ones in this case, are called coefficients. Coefficients, they are the ones that give you information about how many of each of these individual things are reacting or forming within this particular reaction. Okay, so the coefficients are the big numbers. The subscripts are the little numbers, and the big numbers out front tell you how many of either that atom, if we're talking about carbon here, or that molecule are reacting. So one carbon reacts with one oxygen molecule to form one carbon dioxide molecule. And we'll get into more detail about what those mean kind of in a broader context later. But for right now, just that we're talking about symbols, let's just focus on that. Okay, so those are the numbers. The other thing that we see is going on in terms of symbols here are these little symbols that are in parentheses. We have an S and a G and a G. And these little symbols are our different phases of matter. Now we talked about 3 different phases of matter, so we could probably guess that the S in the prior reaction stood for solid, which means that solid carbon was forming. An L in parentheses here means that it's a liquid. We didn't see one of those in our examples, but we'll see some in others. And the G stands for the gaseous state, or the fact that we have a gas present, so our oxygen in that reaction or the carbon dioxide. Now the other option that we have for phases of matter, and this is kind of a new one here, is AQ. If we have AQ in parentheses, that means that it's aqueous, and this goes to what we were talking about with solutions, because aqueous means that the solvent in the solution is water. So the compound itself is the solute, and water is the solvent. You could probably have guessed that just from the word aqua or aqui. This kind of prefix usually refers to water. So it's aqueous, which means that it's a solution with water as a solvent. Okay, so whatever it is that that AQ is next to is in a solution, and we'll look at some examples of that as well. Okay, so let's look at another example. Let's look at the formation of water, speaking of water. So to form water, we need hydrogen gas. Hydrogen, again, is diatomic, like we've talked about. We react it with oxygen gas. And under the right conditions, the hydrogen and the oxygen will react together and form water, liquid water. Okay, and that's at a specific temperature under given conditions, but we'll get into details like that later on. Okay, so here's our H2. The subscript tells me there's 2 hydrogens in this molecule, there's 2 oxygens in this molecule. My water says that there's 2 hydrogens for every 1 oxygen in this molecule. Okay, if we look at our phases here, the G is for gas. We're reacting together 2 gases to form liquid water. There's our L in parentheses. Now if I look at this reaction is not quite complete, because just like a mathematical equation, whatever I have on this side has to equal or balance out with whatever I have on this side. And if I look at the number of things that I have on each side, so if I kind of do a little quick accounting of how many hydrogens and how many oxygens I have on each side, I have 2 hydrogens, 2 oxygens, okay? And if I go on the other side of my arrow here, my arrow is kind of like my boundary. I look at my hydrogens, I have 2, so I have 2 on this side, 2 on this side, that's good. And I look at my oxygens and I only have 1 on this side. 1 on this side, 2 on that side. So this reaction cannot be. It at least cannot be in the form that it's in right now, because I need to have the same number and type of atom or element on each side of the equation. And the reason for that goes back to Lavoisier's law of conservation of mass. Which we talked about in a couple different contexts. The law of conservation of mass said that whatever it is that we start with in a chemical reaction has to be whatever we finish with, or that matter cannot be created or destroyed. So I like to think about that and revisit that, at least in terms of chemical equations, as whatever it is you start with has to be whatever it is that you finish with. So we have to have the same number and type of element on each side of our reaction. Now I cannot change my 2 here. I cannot change my 2 here. I cannot change my 2 here. I can't just make water H2O2, right? Now I have 2 oxygens, 2 hydrogens. I can't do that. And the reason that I can't do that is this is a different compound. This is water. This is hydrogen peroxide. So these are 2 different compounds, and you would be very sad if you went to drink one of them thinking it was the other, right? So this is not a thing that we can do. We can't change the subscripts. We can't change the little numbers, but we can change the big numbers out front. So right now there's no big numbers out front, and I'm putting kind of a dash here or an underline just to show that this would be the place where we'd put those big coefficients. And if we have to have the same number and type of thing on both sides, then whatever is in the front here, these coefficients act as multipliers. So it will multiply by everything that's in the compound. So if I put something in front of this water, for instance, maybe a 2, then now that gives me 2 times 2 of my hydrogen and 2 times 1 of my oxygen. So now I have 4 hydrogens on this side and 2 oxygens, and 2 hydrogens on this side and 2 oxygens. So now my oxygens are balanced, but my hydrogens are unbalanced. So I need to add a 2 in front of my hydrogen, and now that acts as a multiplier as well. 2 times my 2 is 4. And 2 times 1, essentially, if there's no coefficient here, that means that it's a 1. If you would like to put a 1 in the blank, that's totally fine, but not necessary, okay? Now, when I look at this, I have 4 hydrogen here, 4 hydrogen here, 2 oxygen here, 2 oxygen here. I'm balanced. I have the same number and type of element on each side of my reaction, and so the law of conservation of mass is satisfied. So let's look at some other examples. What we're practicing here, this skill that you're getting, is something that you always will get out of a chemistry class, and that's balancing chemical equations. Balancing chemical equations. And when you're balancing, again, you can't change the subscripts, but you're changing the coefficients. So whatever it is that you have on your reactant side, that's the stuff on the left, has to come out and have the same number and type of elements as on the right or on the product side. So we can change the coefficients in order to balance it out. Okay, so let's look at another example of that. Let's do another. So if we take hydrogen and nitrogen, hydrogen gas and nitrogen gas, when we react them together under the right conditions, and it takes a lot of pressure and temperature for these guys to react together, but when you do, then they form ammonia. Do you remember ammonia? Ammonia is NH3. That's the one that we knew our common name for. It's not nitrogen trihydride, it's ammonia, because that's the common name for it. This reaction is going to be really important when we see our historical chemist presentation on Fritz Haber. Fritz Haber was the one who figured out a process to make ammonia from hydrogen and nitrogen in our atmosphere. Okay, so we'll talk about that later. But if we've put our blanks in front of our different reactants and products, then the way that I usually like to do this, and there's a couple different ways to go about it, I like to put a line down the middle and figure out what I have on each side, just like we did with the water. So I kind of like to do an accounting. In these reactions, I only have 2 elements, hydrogen and nitrogen. On this side, I only have hydrogen and nitrogen. You'd know that something was amiss if you had elements on one side that weren't on the other, right? That would just be something that can't exist because of the law of conservation of mass. So let's figure out what we have. There's 2 hydrogens here, that's what that subscript tells me. And there's 2 nitrogens here, that's what that subscript tells me. On this side, I have 1 nitrogen. There's no subscript, so that just means that there's 1, and 3 hydrogens, okay? When I list these out, I like to list them out in the same order on each side, regardless of the order that they come in on either side, because then you can just compare straight across. I have 2 hydrogens on this side, 3 hydrogens on this side, nitrogens on this side, nitrogens on this side. So there's a visual comparison. This one's off and this one is off. So I'm going to have to do something about that. If we start from the beginning here, so if I look at my hydrogens, I have 3 on this side, 2 on this side. Now when we saw this before with charges on ions, we said that we think about this like the lowest common multiple, right? I need to think about the thing that 3 and 2 both go into, which we found before, of course, is 6. So if I multiply this whole thing by 2, then 2 times my 3 hydrogens, remember this acts as a multiplier to both things, 2 times 3 gives me 6 hydrogens, 2 times my 1 nitrogen gives me 2 nitrogens. And again, the way that I like to do my accounting here is I like to cross out what I had to start off with, and then once I make a change, I show what the change did to everything on that side that was impacted. Now if I go to the other side, hydrogen has 2, I'm trying to get to balance to 6. So again, the lowest common multiple means that I need to multiply that H2 by 3. That gives me 6 hydrogens. And it didn't impact the nitrogen. This is just in front of the hydrogen. Now I have 2 nitrogens on this side, 2 nitrogens on this side, 6 hydrogens on this side, 6 on this side, and I'm balanced. And again, if I wanted to leave this blank, then I could, because it indicates that it's a 1, or I could fill it in as a 1 and that would be fine too. So now that you've balanced it out, it says that 3 hydrogens react with 1 nitrogen to give you 2 ammonia. Okay, and that's your balanced chemical equation. Okay, let's look at another example. If we take nitrogen monoxide gas, under the right conditions it can decompose to form dinitrogen monoxide, this is another gas, and nitrogen dioxide. And if we put our lines in front to show that we're going to be balancing this out, then I need to see what I have already on both sides. Now the point that this one illustrates that we haven't seen yet is the fact that we can have elements that are in multiple compounds, right? I have nitrogens and oxygens in this one and in this one. And I have to account for all of them when I'm figuring out what I have on each side. So on this side I have 1 nitrogen, 1 oxygen. That's all there is in this compound, 1 and 1. When I look at this compound, I have 2 nitrogens, and I have to add to it the nitrogen from this compound. So total on this side, I have 3 nitrogens. If I look at my oxygens, I have 1 in this compound and 2 from this. So total on this side, I have 3 oxygens. So in order to balance out this equation, I have 3 on this side, I need 3 on this side. I have 3 on this side, I need 3 on this side. So this is actually going to be pretty straightforward. If I multiply this whole thing by 3, that multiplies by both of them. So now I have 3 nitrogens, 3 oxygens, and I'm balanced, okay? And if I wanted to put them in, I could put that I have 1 of these guys and 1 of these guys. So 3 nitrogen monoxide will decompose to form 1 dinitrogen monoxide plus 1 nitrogen dioxide. Okay, that's what that reaction tells me. Okay, let's look at another example where we have a few more elements to play around with. So far we've just been playing around with 2, but we can have as many as we want. We can get as complicated as we want. So let's look at another example. If I take sodium hydroxide and lead chloride, lead is Pb, remember, we don't want peanut butter in our lead. When I react these together, then I form lead hydroxide and sodium chloride. And I ran out of room there, so I'm gonna put that off to the side. So these are my reactants, these are my products, okay? Now I need to figure out what I have on both sides of my reaction. So I'm gonna give myself some space down here to do this. And I'm gonna list out all of the elements that I have on each side. Okay, so I have sodium, I have oxygen, I have hydrogen, I have lead, and I have chlorine. Okay, and on this side I have sodium, I have oxygen, I have hydrogen, I have lead, and I have chlorine. Okay, so I need to figure out how many of each of the elements I have. And I'm going to show you this, and then I'm going to show you kind of a shortcut. Okay, so again, there are many ways to go about balancing chemical equations, and this is just one of the ways. And going through and doing this accounting on both sides is good as you're practicing doing these for the first time. So let's figure out what we're starting with. On this side, I have 1 sodium, 1 oxygen, 1 hydrogen. That's in my sodium hydroxide. I have 1 lead, and I have 2 chlorines. On this side, I have 1 lead. This 2 here on the outside, this subscript says that I have 2 hydrogens and 2 oxygens. So it acts on the outside as a multiplier because this whole thing is in parentheses. So 2 oxygens, 2 hydrogens. Then I have 1 sodium and 1 chloride. Okay, so if I compare where I have differences, sodium I'm good, and then oxygen I'm off, hydrogen I'm off, lead I'm good, chlorine I'm off. So I'm off for 3 different areas, and that's why I like to line them up like this, because it's really easy visually to go back and forth. So one place that you may want to start is with your chlorine. That's the only thing that's different on the reactant side. And again, you can start anywhere you want. You can go back and forth. And you can also make mistakes. You could start somewhere and end up with the wrong thing, and that's okay. You can just erase it and start back over again. That's the good thing about balancing chemical equations, because you can always go back and check where you're at, how many you have on each side. But I'm going to start with chlorine just because it's the one different thing on the reactant side. That's my logic there. So I have 2 on this side, but only 1 on this side. So I need a 2 in front of my sodium chloride. Sorry, I didn't put my phase there. That's aqueous. 2 in front of my sodium chloride acts as a multiplier. 2 times my sodium, so that changed that. 2 times my chlorine, that changed that. Okay, now I fixed the problem of the chlorine, but I've messed up my sodium. So now I can go to the other side and say, I had 2 on my product side, I need 2 on my reactant side. So maybe I multiply this by 2. Now when I multiply that by 2, it fixes my sodium. Now I have 2 times my oxygen, and I have 2 times my hydrogen. And now if I look to see where I'm at with the rest of these things, 2 and 2, 2 and 2, 2 and 2, 1 and 1, 2 and 2. Great, so I'm balanced. It means I have the same number and type of thing on both sides. Okay, so one of these guys, one of these guys. Now another way that you could have done this, and this is why we learned about polyatomic ions. Remember polyatomic ions? Of course you do. Polyatomic ions were these groups of atoms with a charge on them, and if it stays as a group on one side to the other, meaning that it starts on one side as hydroxide, say, which is our polyatomic that we recognize from here, and it stays as hydroxide, so it doesn't split apart into oxygen and hydrogen and something different, but it stays as OH on each side, we can keep those polyatomic ions as a unit. So if they don't change going from reactants to products, then we can keep them as a unit. So I'm going to put this down here as if, and I'm going to have to go back and forth a little bit, but that's okay. So our sodium hydroxide, if we had sodium instead, and we kept the hydroxide, then that kind of simplifies things a little. Instead of having oxygen and hydrogen, I have an OH here, okay? And now I have lead and chlorine. And I could do the same thing on the other side. Sodium, hydroxide, lead, and chlorine. Okay? Alright. So, if I look at my reaction then, I'm considering my hydroxide as a unit. I have 1 sodium and 1 hydroxide. So when I'm doing my accounting down here, 1 and 1. And then I still have 1 lead and 2 chlorines. That hasn't changed. If I look over here, now I have lead, that's 1 lead, and now I have 2 hydroxides. Remember, the 2 on the outside acts as a multiplier to everything that's on the inside of this, these parentheses. So if I have a hydroxide inside my parentheses, that means I have 2 of those hydroxides. And I still have 1 sodium and 1 chlorine. So 1 sodium, 1 chlorine, 1 lead, 2 hydroxides. Okay, so that kind of changes the way that we're thinking about things, and in some way simplifies, right? Because now I can look at this and say, well, I'm going to need 2 hydroxides on this side and 2 chlorides on this side. So maybe I would have started with the hydroxides, and I would have said, okay, well, I need 2 of these guys then. 2 times my hydroxide will give me 2. That gives me 2 sodiums, and I'd put 2 of my chlorides here to balance out the 2 on that side. So that's just another way to think about this. It's 2 ways of going about doing the same type of problem, and you end up at the same spot, and you can always be checking your work because you know how many elements you have on each side. Okay, let's do one more example. And this one's going to feel kind of easy after that one, but I think it's good just for a little more practice, and hopefully you're working along with me at home. If we take iron metal, and we react it with oxygen. We talked about earlier how when we put iron outside and it reacts with oxygen and water in the air, then it reacts and forms rust, and that's iron oxide. So this is the chemical formula that shows this process. Okay, this is the chemical reaction. So this is the chemical formula for your rust, iron oxide. And these are your components. These are the reactants that react together to form that rust. Okay, and it's solid iron with a gaseous oxygen gives you solid rust, if you want to think about it that way. Okay, so let's see what we have on both sides. We just are back to 2 elements on each side, so that probably feels a little bit easier, especially after the last one. And on this side, we only have 1 iron. It's just the 1 iron that's reacting with our 2 oxygens. That's our diatomic gaseous oxygen. And on this side, we have 2 irons and 3 oxygens, right? And these come from our subscripts. So when I'm looking at these guys and I'm trying to figure out where to start, I have problems on both sides, right? I have 1 iron here, 2 irons here, I have 2 oxygens here, 3 here. Now you might be tempted to say, well, what if I put 2 in front of my iron? And that's not necessarily a bad thing. Now that balances out the iron, but it doesn't do anything to solve the oxygen problem. And the oxygen problem really comes about because I have an even number on one side and an odd number on the other. And so anything that I multiply my oxygen on my reactants by is going to give me an even number. So I can never have an odd number of oxygen and have this reaction balance out. Does that make sense? So if you are multiplying anything by this 2, then you have to have an even number of oxygen on this side, which means that you're going to have to get this to an even number of oxygen on this side. And the quickest way to do that is by multiplying by 2. So if I multiply by 2, then that gives me 2 times my 2 iron here, which changes it to 4, and 2 times my 3 oxygen, which changes it to 6. Now this is an even number. And now I can balance it out by making 3 oxygen on this side. 3 times my 2 is 6. And now when I look at what's left over, I have 4 iron on this side, but only 1 on this side. So I need 4 there, and now I have 4. Now if I would have jumped to the conclusion of starting with 2 here, I would have had to change my 2 to a 4 in order to balance it out, right? I could have started that way, and that's totally fine. But you'd have to make sure that you're changing things along the way in order to get it to a balanced set. So you need to have the same number on each side when you're done with your equations. Okay? If you have any questions on this, let me know. Otherwise, I'll talk to you next time.